So we want to talk about Euler characteristic and the Betti number. For any simplicial complex K, where the simplices are denoted with sigma n, that is an n simplex, we can define the number function n of sigma n, that is equals to the number of n complexes in K. So this number function computes how many n complex or n simplexes are inside K. Okay. Then the Euler characteristic is defined as psi of K is equals to, let psi equals to 0 to infinity, because you can take a large number of it, so that's why I'm putting this to infinity. Actually, this is how it is defined. Then I multiply this with the number operator on my simplices. That actually counts how many n simplexes are there. Now let's call this thing as our definition and let's try to see it. And our claim is that, again, that this is independent of triangulation. So you can easily see that if you apply this on R3, you can easily recover that formula that we had earlier, that is V minus E plus F, that is vertices, edges and faces, because vertices are just sigma zeros or 0 simplexes, edges are sigma 1 simplexes, faces are sigma 2. Okay, so let's take a very familiar example, which is a solid filled in triangle. Let's give it an orientation like this: P0, P1, P2. The simplicial complex is something like this: P0, P1, P2, and we have P0 is going anticlockwise, right? So this is P0, P1, we have P1, P2, we have P2, P0, and we have a 2 simplex as well. So this is P0, P1, P2. So how many 0 simplices are there? Sigma 0, that means n of sigma 0 is 3. N of sigma 1 is what? 3. N of sigma 2 is just what? 1. And all the n sigma n is 0 where n is greater than 2, right? Or you can write it as equal greater than 3. So according to the definition of this Euler characteristic, this simplicial complex has the sum over I from 0 to infinity minus 1 over I n of sigma I, and I write it as n sigma 0 minus n sigma 1 plus n sigma 2, right? This is just 3 minus 3 plus 1. Did I do it rightly? Yes, 3 minus 3 plus 1 equals to 0, because 3, 3, 1 is 0, right? And you can easily compute the Euler characteristic with this vertices minus edges plus faces. How many vertices are there? 3 vertices. How many edges are there? 3 edges. How many faces is there? 1. And you see that these two agree. Okay? Oh, I wrote it as 0. No, it's not 0. Sorry, it's 1. My mistake. And you know that this triangle is actually homeomorphic to a solid disk as well, right? So we wanted to show you that this Euler characteristic is independent of triangulation as well. So instead of taking this triangle, let's take the disk and let's have a triangulation of the disk. Okay, one possible choice of a triangulation of a disk is something like this. We have one triangle, another, and another over here, and another like this. Okay, and these are all filled in. And let's denote these points in a more bolder color so that we can easily see things. Okay, because I can continuously deform it and take this guy back to this disk, right? You can even put more things over here, but let's keep things up to this part. So how many vertices are there, or so to say, how many zero simplices are there? So I want to compute the number of zero simplices, right? I have 1, 2, 3, 4, 5, 6. 6. How many edges are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 edges. How many faces? Faces is very easy. 1 face, 2 face, 3 face, 4 face. So N2 is 4, right? So my Euler characteristic, and this is a different triangulation. Remember that. So let's denote this triangulation as K prime. So now again I will have this 6 minus 9 plus 4. 6 and 4 gives me 10 minus 9, which is equals to 1. Again I produce 1, so it's not dependent on how I triangulate the space, right? And you can even fill this up, and if you do that, and let's call that K double prime, and you want to compute this K double prime, now you have how many vertices? You have 1, 2, 3, 4, 5, 6. Again, 6 vertices. Okay. You have how many edges? 1, 2, 3, 4, 5. Okay, let's count the outsides first. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have minus 10. How many faces? 1, 2, 3, 4, 5. Again, 11 minus 10. What is that? This is just 1. Now you see, it really doesn't matter what sort of a triangulation you are taking. Your Euler characteristic will always be independent of a triangulation. With that, let us conclude the long discussion on the Euler characteristic that we have been having so far. And since our Euler characteristic is tied to the homology groups, to see this relationship, we can define something called a Betti number. So why do we define this Betti number? To see how our chi, that is the Euler characteristic, is connected to homology groups. Okay, so we define the Betti number. Let's say Bn of k of some simplicial complex as the dimension of the nth homology group. We define the Betti number Bn of k as the dimension of the nth homology group, and mathematically you can write it as the Betti number Bn of k is just the dimension of your Hn of k. Now what does this dimension mean? It means that your Bn of k is the rank of the free abelian part of Hn of k. Okay, and the Euler Poincare theorem that we talked a lot earlier relates the Betti number with the Euler number in the following manner, that is given by, so this is the Euler Poincare statement that relates the Euler characteristic of some space K, or so to say a simplicial complex or the triangulation of some space, that is denoted by K, and this is the summation would be n of k, where the n runs from 0 to infinity. Okay, so since we haven't talked about what is a free abelian group, I really don't want to discuss much further. When we talk about free abelian group, maybe we'll do some computation with Betti numbers as well. And this concludes our discussion on the entire homology lectures. From next lecture we'll try to see what are homotopy, and we'll see at the end of homotopy lectures is that what we do in homology is that we look for holes. That was our initial motivation for doing homology, and homotopy is another way of finding holes. And at the end of the homotopy lectures we'll try to see some relation of the two ideas that comes in the name of homotopy and homology.